this video, we'll look at a few questions. One pertaining to stability. The other two questions we will be looking at will be this principle of moments, but it will be another version, which I find quite interesting. Okay, for stability questions, we're looking at is for this question is about a person standing next to the wall. Okay, and you'll find that at the particular instance, the question will state that the boy, when he raised his left foot, okay, he will lose balance, and the question will ask the student to explain this particular phenomenon, these particular explanations. Okay, for this type of question, okay, the student need to know that when the question talking about stability, the first clue about the question dealing with stability is when the question asks about balancing but not balance. Okay, this is usually the clue whereby the students is clue for students to say that the topic going to be tested will be on moments or even on stability. This is how we actually narrow down from all the 22 topics down to this particular topic and these particular keywords. Okay, so now let's look at the question part by part, one part at a time. Okay, part A, the question asks for standard definitions of CG, center of gravity. In your answer, please take note. Okay, you need the keywords. Okay, the keyword for stability is what we call seems to act. Is whereby it's a pseudo point whereby we just classify the entire weight seems to be acting on this particular point, this pseudo point. Okay, this point, this pseudo point. That's why the one important word that we're looking out for is the word seems to act or appear to act. Okay. For part B, the questions look at how he cannot raise his left foot without losing his balance. When we talk about stability, cannot losing his balance, it means that this particular observation or this particular situation you are looking at is unstable equilibrium. Okay, whereby the student or the object unstable equilibrium. Okay, whereby the object, in this case the boy, he is unable to recover from the action. Okay, to recover back to his original position. That's why he always lose balance. Okay, so when we talk about unstable, the same three words that we're looking out for. Your answer key need to mention about the force. Answer need to mention about the perpendicular distance, and followed by the moments, the related moments, and the actions. Okay. If you forgot about this, you can look at the video that I have on stability. Is on 5.4. Okay, on chapter 5. Okay, on the keywords that we have on stabilities. Okay, so when we talk about force, the common thing that we have is you can either talk about the line of action of the force, okay, or you can talk about the force himself. In this case, it will be the weight, okay, and whether is it within or outside the base area. For unstable equilibrium, usually is outside the base area, whereby when I lift my left foot, the pivot will be on the right foot only. The right foot will act as a pivot. This area here will be the base area that we are talking about, the base area. Okay, so when I lift my left foot, my weights, okay, it will be still at the same place, right from the CG pointing downwards. It will be outside the base area of the house, of the foot, okay, outside the pivot, okay, outside the pivot, or on the right side of the pivot, or outside the pivot. And there is a perpendicular distance between the pivot and the right foot. Okay, so this will be the second point. Okay, the perpendicular distance between the pivot and the weight and the force itself. And what does it do? What does it do? It will actually create a clockwise moment, okay, about the pivot, and this clockwise moment, okay, will actually cause the object, which is the person, to actually lose balance, okay, which is the action. Okay, so when we talk about stability, we always look at the four keywords, okay, that we use to tackle this particular concept. Okay, the force, the perpendicular distance, the moments, and followed by the action. Okay, in this particular manner here. Okay, if the keywords are still unsure, you can refer to the video at 5.4. Okay, to see the detailed write-up of the keywords. Okay. As for the other question that we're looking out for is question 1. Question 1 for this particular quick check, okay, 5.5, is a standard question of using principle of moments because the ruler is in equilibrium. Yeah, but what is interesting is that there is actually two forces here. One is the 60 Then after that what you do is, okay, so the mass will be 0.06 kg, change from 60 gram to kg. Then after that, remember, this is the mass, the weight of the object. Then the other force that we are looking at will be actually the weight of the ruler. Okay, because they mentioned the question here, there's a weight of the ruler. Okay, weight of the ruler for uniform rod, okay, it will be in the middle. Uniform means it's a balance, it's all shapes, regular shapes, meaning the CG will be in the middle of the platform. Okay, the uniform in this case, it will mean that a 1 meter rule, the weight, the CG will be at the 50 cm mark. This is where the weight will act. Okay, and this is what we mean by CG. Okay, the CG will be the point, and the point will be at the middle of the ruler, and this is where the weight will actually act on. So between the weight and the pivot, the weight will actually generate a clockwise moment. As for the object, okay, the 0.6 kg object, he will actually generate another moment to actually balance the object, because the question says it's in equilibrium. So it will actually generate an anti-clockwise moment to balance out. Okay, remember the object we are looking out for has a weight. Okay, the weight is, okay, 0.6 Newton. Okay, remember, weight is mg, so the formula that we are using here is weight is mg. If the mass is 0.6, g is 10, you substitute these two numbers inside, you get 0.6 Newton. Okay, so this will be the weight of the 60 gram, okay, which is 0.6 Newton. It will create an anti-clockwise moment. So now, since they are balanced, the anti-clockwise moment will actually be equal to the clockwise moment. Okay, and the clockwise moment will be the weight, and the perpendicular distance will be between the pivot and the force. Okay, it will be a 20 mark and the 50 cm mark, which is 30 cm mark, which is 0.30 meter. Okay, so this will be the D perpendicular, or the first one. The second perpendicular distance we are looking out for is actually by the 0.6 Newton force object. Okay, sorry, it's object. So the perpendicular distance will be from the 5 cm mark to the 20 cm mark. So the perpendicular distance we are looking at for is actually at the 15 cm, which is 0.15 meter. Okay, so once you have this equation, you'll find that the next step will be a simple algebra where we solve for W, and you'll find that the weights here will be 0.3, or the answer here will be 0.3 newtons. Okay, but take note, the option given here is all in grams. Okay, so 0.3 Newton. Okay, so please make effort to convert it to kg first. You divide by 10. Okay, it will be 0.03 kg. Then after that, convert it further to become 30 gram. Okay, that will be the answer they are looking out for, which is D. Okay, so the same approach that we are looking. Okay, whereby you have the clockwise moment and anti-clockwise moments. Okay, after that you look for the perpendicular distance, and then you equate both moments together, because the question says it is in equilibrium. Okay, I hope this clarified most of the doubts, or all the doubts you have on principle of moments. Okay, and before we end, we look at the last question, which I find quite interesting, which is similar to the question that I have in my previous video, whereby you have multi-layer rods balancing. Okay, in this case, the approach will be the same. Okay, always look at it layer by layer. Okay, at the bottom layer here, okay, same thing. There's two objects, there's wave 0.6 and 0.16, which means the total weight at this layer is actually 0.76 Newton, a combination of everything. As for the other layer on the other side, okay, the total weight we are looking out for will be R plus S. This will be the total weight acting on this particular side. Okay, so once you have the weight, then the other one you need to be careful is that the weight applying at this layer, at the second layer, will be the weight experienced by this thing. So at this junction here, this will be the total weight experienced by the rod, which is 0.76 Newton. Okay, so on this side, the total weight experienced here will be R plus S. Okay, same thing at this bottom layer. Okay, likewise for the forces, now we look at likewise for the forces, when we look at moments, we also look at it layer by layer. So if you look at the moments on the left side at this particular area, the rod 1 will be pivoted at this particular point, and there will be two moments acting about this point. One will be by the triangle, which is 0.16, which is clockwise moment. The other one is the anti-clockwise by the circle, by the ring. Okay, so we look at the moments at this rod 1, we treat it separately. So this will be what the question 1 is actually asking. Okay, how to find the D. So we look at rod 1 as individual. So the forces on rod, the moments on rod 1 due to force P, okay, the perpendicular distance is D and the weight of P is 0.6. So this will be the total anti-clockwise moment on rod 1, and this will be the moments by object Q. Okay, 0.16 Newton, and the force will be 4 cm. Remember, convert it to meter first. Okay, then after that, balance, since left clockwise and anti-clockwise moment are the same, you'll find that the distance D can be found using the algebra. Same thing, how to find R and S. R and S, you'll find that how I know R and S is that same thing, the clockwise and anti-clockwise moments will be the same, and both of them have equal perpendicular distance. And when I have equal perpendicular distance, I will actually know that the forces on each of them are actually the same, which means that indirectly I can say that since the rod here is balanced, okay, the distance here is also balanced, I can further infer that the anti-clockwise moment on the left and the clockwise moment on the right would be balanced. And since both moments have the same perpendicular distance, which is 10 cm, the force on the left hand side here, the force on the left hand side, okay, would be the same magnitude as the right side. So which means if the force on the left is 0.76, okay, the right side will also be 0.76 Newton in total. Okay, and since on rod 3 we know that the total force acting on rod 3 here, total force here will be 0.76 Newton. Okay, and R and S has equal weight because R and S, the moment by R and the moment by S is the same, and they share the same perpendicular distance, which means weight of R and weight of S will be the same, and both of them will add up to be 0.76. Oh, sorry, this is not R. Sorry, this is the total. Okay, so since R and S will add up to be 0.76 and they are equal, so which means R will take half of the number, S will take half of the number. Okay, so which means the R will be 0.38, S will be 0.38. Okay, okay, so I hope this is clear. Okay, because the moments at both sides are equal and the distance are equal, so that's why the forces experienced by R and S will actually be the same. Okay, same thing, what happened at last part is what happened when Q fall off. Okay, when Q fall off, okay, when Q fall off, okay, you'll find that the rod 1 will actually be unbalanced, because the only moment now I have at rod 1, okay, there's only one moment, which is P, which is the anti-clockwise moment. Okay, so that's why for rod 1, okay, I will have a anti-clockwise moments, and rod 1 will actually drop off. And because now, okay, the total, because my Q has disappeared, the total force at this at rod 2, okay, the total force here on the left side will actually be lower, okay, as compared to the force on the right side. Okay, so now my force on the left side will be smaller than right side. Remember, originally both sides are the same, but now they are not the same. Left is smaller. So as a result, you'll find that my rod 2 will actually rotate clockwise, because the moments on the clockwise moment on the right side is actually larger. Okay, I do hope this is clearer for you. Okay, if not, you can look at the video